Aloha BioChem. In this video, we continue Chapter 3 and discuss ions. So this time we cover section 3.2 on ions, and we also take a look at polyatomic ions. Let's first recall what we did in our previous lecture when we compared ionic compounds with covalent compounds. Covalent compounds are made of tiny particles called molecules, and the atoms inside the molecule are held together through what are called covalent bonds. And these compounds combine non-metal elements only. Here's a simple example of a covalent compound called hydrogen fluoride with the formula HF. So you can see the elements are combined in a 1-to-1 ratio. For every one hydrogen atom, there is one fluorine atom. So that's the ratio right there, fixed ratio. We can have a look at the Lewis dot structure of the molecule as follows. To draw that, we write the Lewis dot structures of the atoms, hydrogen and fluorine, separately. So hydrogen gets one dot because its electron configuration is 1s1, but you could also use the periodic table and see that hydrogen, being in group 1a, would have one valence electron. All of the elements in group 1a have one valence electron. And doing this for fluorine as well, fluorine gets 7 dots because that's its electron configuration. It has 7 valence electrons, so it gets 7 dots, but fluorine likewise is in group 7a. So that tells you also that it has 7 valence electrons and gets 7 dots. So with the dot structures of the atoms, the way these atoms combine are through the sharing of their unpaired electrons. You see hydrogen's single valence electron and fluorine's single unpaired valence electron. The other ones are paired up. They can't be shared. But this one can be shared, and then these two electrons form a shared electron pair between the two atoms. And that's what a covalent bond is. You see, after the electron pair is being shared, hydrogen is holding on to that pair and fluorine is also holding on to that pair. So if they're both hanging on to the same pair, then those atoms are now linked. So both atoms hold on to the same electron pair. Notice also that hydrogen, after sharing, by sharing, it's kind of like it gains another electron, and so it now is associated with 2 electrons, and so you could say that it sort of has the electron configuration 1s2, and that's the same electron configuration as the noble gas helium. So helium is element number 2, and likewise fluorine, by getting to share hydrogen's electron, it sort of gains 1, and its electron configuration is now like 1s2, 2s2, 2p6, and that's the same configuration as the noble gas neon. So you see that bonding principle at work. Atoms like to gain, lose, or share electrons in order to attain the same number of electrons as a noble gas has. So hydrogen becomes like helium, and fluorine becomes like neon, and that's the bonding principle. We can take a quick look at a model of hydrogen fluoride. Right there you see the ball and stick model and the space filling model, your hydrogen and your fluorine. So models are helpful sometimes, and we'll be making quite a bit of use of them, and also quite a bit of use of these Lewis structures, especially in the next chapter. So let's compare ionic compounds with covalent compounds now. Whereas covalent compounds are made of molecules, ionic compounds are formed from particles called ions. And these ions are held together through what are called ionic bonds. And these compounds combine both metal and nonmetal elements. So they're pretty easy to recognize. Just see if the formula has a metal in there. So lithium fluoride is an example of an ionic compound. So you see the metal lithium combined with the nonmetal fluorine. This is also in a 1-to-1 ratio, so a simple formula. And we can get a better understanding of ions and ionic bonds by also drawing the dot structures of the atoms first. So lithium is and also in column number 1, so right below hydrogen, it's in group 1A. So I'll point that out to you. Lithium is right there below hydrogen, so 1 valence electron. It's got 3 electrons total, 1 valence electron, and so here's its electron configuration, but it's got that 1 valence electron. It gets 1 dot. Fluorine, we just saw fluorine, so it has its 7 valence electrons and 7 dots. And these are the dot structures of the atoms. Now what happens this time is electrons are not shared, but one of them is transferred all the way over to the other one. You see, lithium loses its electron and it goes all the way over to the fluorine. And in doing that, it becomes a positive charged cation. So a positive ion. You see, if it loses an electron, it's no longer neutral in charge. It has 1 less electron, so it's now positive charged. And look at its electron configuration. When it loses that valence electron, it's left with 1s2. So lithium, by losing an electron, becomes like the noble gas helium. And then fluorine, again, by gaining an electron, not through sharing this time, but by gaining it completely, it goes all the way over to fluorine. It becomes negative, and it's a negative anion, and its electron configuration, again, becomes like that of neons. So you see, ionic compounds are made of ions. And when you have opposite charged ions, opposite charges attract each other, of course, and that's what an ionic bond is. It's opposite charged ions attracting each other, and so that's what this represents. There's a physical attraction between them, and that's what holds lithium ions and fluoride ions together. So covalent compounds are made of molecules. Ionic compounds are made of ions. And I'll show you a formula for lithium fluoride here. So here it is. So you can see ionic compounds always have this beautiful ordered structure. So the lithium cations are the small purple ones, and the fluoride ions are the large green ones, and you know, so these are the particles that make up this substance. Okay, there are no molecules in here. It would be incorrect to say that these two are a molecule and then those two are another molecule. Because someone else could come along and say, well, what about those two? Maybe those are the this one is a molecule and that's another molecule, and LIF. Well, you'd both be wrong, okay? There are no molecules in here. The tiniest particles are ions, and you always have positive ions and negative ions in an ionic compound. See, the structure is neutral because you have the same amount of positive charges as negative charges, okay? So maybe you can get a better understanding of the ordered structure right here. But this is the ball and, not really a ball and stick model, just like a ball model. And but here's the space filling model. Well, one thing we also mentioned in our previous lecture is that cations are a little bit smaller than the atoms from which they are formed. So a lithium atom, after it loses its electron, that nucleus is able to draw in the electron cloud even closer. You see, lithium's nucleus hasn't changed. It has 3 protons. And after it loses an electron, it's able to draw in the electron cloud even closer. You have less electrons than protons, so the larger positive charge pulls in the electron cloud even closer, so the cation is smaller. And the opposite occurs for anions. They are larger than their atoms because that positive nucleus isn't able to draw in more electrons. You know, it's able to draw in less electrons closer, but if you gain an electron to become an anion, you know, the electron cloud gets a little bit bigger. So be aware of that. Let's take a look at a couple of more examples. Another one is magnesium iodide. Magnesium iodide, this substance is also called magnesia. I didn't write the formula for this, but it's MgO. So 1 magnesium for every 1 oxygen, MgO. And the dot structure for magnesium is Mg with 2 dots. You see, magnesium is in group 2A, so there are 2 valence electrons. Here's its electron configuration, and I'll point out magnesium to you here. So it's in group 2A. All the elements in group 2A have 2 valence electrons. Now it's got 12 electrons total, but 2 of them are valence electrons. All right. And then oxygen has 6 valence electrons because it's in group 6A. You can see oxygen over there. All the elements in group 6A get 6 valence electrons. It's got 8 total, but 6 of them are valence. And so there's oxygen's dot structure, and you can see its electron configuration as well. Now again, this is an ionic compound because you have a metal and a nonmetal. So we know that electrons are going to be transferred, and they're going to be transferred in such a way so that the atoms achieve the same number of electrons as some noble gas. And if magnesium transfers both of its electrons all the way over to oxygen, then magnesium losing 2 electrons becomes a +2 cation, and it gets that electron configuration of neon. So losing 2 electrons, magnesium becomes like neon. And oxygen, by gaining 2 electrons, becomes a -2 charged anion, and it also becomes like neon. So they both become like the noble gas neon. I wanted to point out that this time we are dealing with a +2 charge ion and a -2 charge ion. So that's a stronger attraction, stronger ionic bonds between these ions than between a +1 charge and a -1 charge. So the larger the magnitude of the charge, the stronger the ionic bonds. I also want to point out that by losing and gaining electrons, the outer shells of the magnesium have what's called an octet. There are 8 electrons in the outer shell. That second shell of magnesium now is the outer shell. It lost the 3rd shell electron, so now all that's left is the 2nd shell. And 8 electrons complete the 2nd shell. And by oxygen gaining 2 electrons, it also fills its outer shell. It gets that octet. So atoms like to gain, lose, and share electrons in order to form a filled outer shell. They want to get that octet. So that's what happened up here with the fluorine as well. You'll see octets quite a bit. Now one more example of an ionic compound, aluminum nitride, and there's no formula right here, but it's again a 1-to-1 ratio, ALN. So to examine the ions and the ionic bonding, let's first write the dot structures of the atoms. Aluminum is in group 3A, and nitrogen's in group 5A. I'll point those out to you. So here's aluminum, it's right below boron. So 13 electrons total, 3 of them are valence. And then nitrogen is element 7, so 7 total electrons, 5 of them are valence. So aluminum gets 3 dots and nitrogen gets 5 dots. So here they are, and there are their corresponding electron configurations. So you can see the 3 valence electrons in the third shell of aluminum and the 5 valence electrons in the second shell of nitrogen. And again, this is an ionic compound because it's metal and nonmetal, so electrons are transferred all the way over. The metals will be the ones that lose their electrons, and the nonmetals will gain the electrons. So aluminum will lose all 3. They'll go over to the nitrogen, and aluminum becomes a +3 charged ion. And nitrogen gaining 3 electrons becomes a -3 charged ion. So this time you have a powerful cation and anion, +3 charge and -3 charge, that forms an even stronger ionic bond as what we saw before. And again, by losing 3 electrons, you can see that filled second outer shell, that octet on the aluminum and the octet in the second shell on nitrogen. So again, that bonding principle at work. Now, hopefully, it's not too much of a stretch to see that there's a pattern in the charges that form. You can quickly identify what type of charge an atom will like to form if it's in an ionic compound. You see, lithium was in group 1A, so it forms a +1 charge ion. Magnesium in group 2A forms a +2 charge, and aluminum in group 3A forms a +3 charge. And fluorine is a -1 charge, oxygen's a -2, and nitrogen's a -3. So this trend right here occurs for many other elements, and I'll point out, the pattern. You see, elements that are in group 1A, they have 1 valence electron, and after losing it, they become +1 charged ions. And those in group 2A, like the magnesium and calcium as well, that's right below magnesium, they have 2 valence electrons, and after they lose them, they become +2 charged ions, and those metals in group 3A lose all 3 valence electrons to become +3 charged ions. Now, the elements in groups 5A, 6A, and 7A, the one in group 5A needs to gain 3 electrons to have that octet. 5 + 3 is 8. So it gains 3 electrons and it becomes a -3 charged ion. And the elements in group 6A gain 2 electrons to get the octet and they become -2 charged ions, and those in group 7A become -1 charged ions. And maybe you can see the pattern a little bit more clearly with this periodic table here. And I'll bring this over and kind of blow it up for you so we can get a better look at it. You see, this is figure 3.2 in your textbook, and you can see the metals, the alkali metals in group 1A, they typically form +1 charged ions. Okay, lithium, sodium, potassium, rubidium, cesium, you'll find these as +1 charged cations. Those in group 2A, like magnesium, calcium, strontium, they like to form +2 charged ions. Aluminum is in group 3A, it forms a +3 charged. And then for the nonmetals, these form the -1 charged ions, the halogens in group 7A. These form the -2 charged ions, and those form the -3 charged ions. So this table will help you just know right away like what the charge on ions is. So if you have another periodic table that doesn't look like this, so here's one that doesn't have the charges on it, just try and remember this is the +1 charged column, +2 charged column, +3, the -1, the -2, and the -3. Okay, so a sulfur ion, if somebody says I have a sulfur ion, it's a -2 charged ion because it's in the -2 column. And if someone has a bromide ion, an ion of bromine, it's a -1 charged ion. Okay. Now these ions are predictable. We know that bromine is going to be a -1 charged ion, and we know that potassium is going to be a +1 charged ion. So those are the predictable ions. Other elements sometimes have ions of different charge, and these are seen especially in the transition metals, and I'll show you some of those other less predictable charged ions. So here are a few of them. Iron, for example, sometimes iron will be a +2 charged ion, and sometimes it'll be a +3 charged ion. If somebody says I have an iron ion, you need to indicate what the charge is. Is it +2 or +3? And gold likes to form +1 ions and +3 ions, and there are several elements that do this. Lead forms +2 and +4. I don't think there is any ions that have greater than a 4 charge. I think that's about the maximum you'll see, and just a couple elements will do that. And so elements in this region right here, this region, they'll form cations. They'll form positive charged ions because they are metals, but their charge is variable and not so predictable. Now, let's do a couple of short, example problems. So suppose you're posed with the following question. Here we'll do problem 3.5. Okay, how many electrons and protons are contained in each cation? So suppose you have this cation right here, Au+. How many electrons and protons are in this cation right there? Remember that Au, that's the element gold. Au, give me back my gold. So all you have to do is look up gold on the periodic table, and that will tell you how many protons it is, because the atomic number of gold is the number of protons, and then its charge will help you determine the electrons. So let's see how this is done. So where is gold? Gold is right there in the copper, silver, gold column. Gold is element number 79. So gold atoms have 79 protons, and if it's got a +1 charge, that means it's missing a single electron. So rather than 79 protons and 79 electrons, it's missing an electron. It only has 78 electrons. And if it's a +3 charged gold ion, then it's missing 3 electrons. So 79 protons and missing 3 electrons would be 76 electrons. Okay, but what about Sn2+ and Sn4+? This is Tin2+ and Tin4+, the element tin after the Latin name stannum. So let's find tin on the periodic table. Here it is. Down there somewhere, it's element number 50. So tin atoms have 50 protons and 50 electrons. But the tin ions, these have lost some electrons. This has lost 2 of them. So 50 protons and 48 electrons. And this one's lost 4 electrons, 50 protons and 46 electrons. So it's an interesting little problem. Now, ions are very important in the human body. This is figure 3.4 in your textbook. So it's good to be aware of some of the roles that they play in biochemistry. Calcium, of course, is important in teeth and bones. Your bones are made with ionic compounds that contain the calcium 2 plus ion. What else? So sodium and potassium are present in body fluids. So like blood has sodium and potassium, and they actually help regulate blood pressure. And you need to have the proper amounts of sodium and potassium, and so you need to take the proper amounts. Usually the foods though have too much sodium, so you end up getting too much sodium in your diet and not enough potassium. If you have too much sodium in your diet, that affects your blood pressure, and we'll talk about how that works when we get into solutions in chapter 8. Sodium, it gets into your bloodstream, and it disrupts your cells, and it causes it causes your blood volume to increase, so the liquid comes out of your cells, and it goes into the blood volume, and that pressurizes your blood system. It's interesting, but it's scary. So you got to watch the amount of sodium that you eat. Iron 2 plus. This is important in your red blood cells. Iron helps carry oxygen throughout the body. The chloride minus ion, you'll find this inside your stomach and gastric juices. It helps break down food in the stomach. And the magnesium 2 plus ion, this is important in nerve transmission and muscle control. So magnesium ions. And there are lots of other ions inside the body. Here are just a few examples. And this table right here, table 3.2, shows you some of the foods that are high in sodium. So potato chips, watch out for them. Hot dogs, ham, smoked chicken, soup, tomato sauce, Parmesan cheese, all the good stuff. And then foods that are low in sodium. Salmon, raisins, cereal, oatmeal, orange juice, banana. So there you go. Now I know this stuff tastes good, but definitely be careful. If you continue to have high sodium in your diet and high blood pressure for a long period of time, that'll strain your heart. And that's going to be a bad thing, especially later on in life. So save yourself. Eat well. Moderate your foods. I want to end this lecture with just a quick look at a special type of group of ions, and these are polyatomic ions. Here is a list of polyatomic anions, and what polyatomic ions are is they're sort of like charged molecules. Instead of a single atom gaining or losing an electron, imagine like a molecule that loses an electron or gains an electron, and the whole molecule becomes charged. That's what polyatomic ions are like. They're kind of like charged molecules. So there are some polyatomic ions that are listed here, and maybe you've heard of carbonate, potassium carbonate. The ionic compound has the carbonate polyatomic ion. So this carbon and 3 oxygens collectively carry a -2 charge. So there are 2 extra electrons associated with this molecule, and so you can ask, well, which one of these atoms gets those 2 electrons? Well, they kind of all are associated with them. And the bicarbonate, HCO3 minus. So this group of atoms, these 5 atoms, collectively carry a negative charge, so have an extra electron. Bicarbonate, sodium bicarbonate, that's baking soda. So sodium bicarbonate has the bicarbonate ion in there. There are some other ones, nitrates and nitrites, good in fertilizer, but not so, well, they have good and bad roles in biochemistry. They can be used for helping preserve foods, but you know, too much can be a bad thing. And so nitrate and nitrite. So again, a polyatomic ion is this group of atoms that are bonded together. You know, it's like a charged molecule. So the atoms that are bonded together are held together through covalent bonds, but collectively there's an extra electron in there somewhere. Okay. So some other ones, sulfate, sulfite, bisulfite. So lots of polyatomic ions in here. Just be aware that you'll see them again, and it's good to have you know, a list of some of the more common ones. There are many more than this, but here are some important common ones, and you want to be able to reference this table when needed. So that's about it for this lecture, actually. Next time we will discuss ionic compounds and how to name them. So stay tuned for that. Aloha.